So far in this class we've talked about ways we can differentiate functions so that we can find the slope of a curve at any given point. In this video we're going to talk about methods we can use to differentiate relations that are not functions. To start out with, we're going to look at this equation here where we have x squared plus y squared equals 25. From previous classes we may remember that this relation here represents a circle with a radius of 5 centered at the origin, and would look something like, well, not that, and would look something like this, where the x-intercepts are at -5 and +5, and the y-intercepts are at +5 and -5. This relation right here does not fit what we've been doing so far in this class because it does not pass the vertical line test. If we were to draw a vertical line, say there at x equals -3, that vertical line would intersect there and there, so we would have multiple values of y for one value of x, and that does not satisfy our conditions for a function. If we were to try to differentiate this now, what we might do is to split it up into two separate functions. We might look at the top half, this top half of the circle here, and the bottom half of the circle here as separate functions. So what we could do is we could solve this for y, and we would end up with something that looks like this. We would have y equals plus or minus the square root of 25 minus x squared. Now, the plus part here would represent the top half of the circle, and the bottom part here, the minus part would represent the bottom half of the circle. So to differentiate this, if we were going to differentiate, say, the square root of 25 minus x squared, we could rewrite it like this. And although we haven't proven it yet, the power rule works when we have rational exponents, not just integer exponents. So we could differentiate this using the power rule as well as the chain rule, and we would get dy dx is equal to 1/2 times 25 minus x squared to the -1/2. And then using the chain rule, we also have to multiply by the derivative of the inside part, which would be -2x. And simplifying that, we would get dy dx is equal to, well, let's see here, we're going to have the 2's cancel, and so we're going to have a -x on top coming from here, and on the bottom we're going to have the square root of 25 minus x squared, so we get -x over the square root of 25 minus x squared. Now we did all of that, and that just gives us the derivative of the top half of the circle. It doesn't give us the derivative of the bottom half of the circle, and we would have to do that process again. It turns out to be a lot of work, and it turns out to be very tedious, and we can find a better method to do this. And that method we're going to use involves the chain rule, which we learned in the last section. So what we're going to do is we're going to differentiate this relation as it is. We're going to take each term and differentiate it. And we're going to differentiate it with respect to x because what we want to find here is dy dx ultimately. So what that tells us is we have to differentiate with respect to x. The chain rule tells us that when we differentiate a function of a different variable, we have to multiply by the derivative of that function with respect to x also. So let's take this to the max here. If we differentiate x squared here, since we're differentiating with respect to x, we would write that as 2x. That's just the derivative using the power rule. And just to get in the habit of doing things right with implicit differentiation here, what I'm going to do is I'm going to say we differentiated the variable x with respect to x. So when we differentiated this x squared here, we differentiated x with respect to x, and we got 2x. Now, this dx over dx here is just going to end up being 1. However, when we differentiate the y squared, we're going to differentiate it like we're differentiating with respect to y. so we would get 2y using the power rule. However, since we differentiated with respect to y and we need to do it with respect to x, we are going to use the chain rule and multiply by dy dx. So what we're saying here is we differentiated y with respect to x. And again, that's just using the chain rule. And then we have to differentiate this term here, the 25. The derivative of any constant is 0. We could say that we're differentiating with respect to any variable really, and it's still going to be 0. So, like we said, this dx here is going to be 1. So what we have is 2x plus 2y dy dx is equal to 0. And at this point, all we really have to do is solve for dy dx, get that by itself. So we can get that by subtracting 2x from both sides, and we get 2y dy dx is equal to negative 2x. And then dividing both sides by 2y, we get dy dx is equal to negative x over y once we cancel out the 2's. This is a much simpler equation for the derivative than we got doing it the old way, and it also allows us to find the derivative of the top half and the bottom half of the circle at the same time. All we have to do now to find the slope at any given point is plug in x and y values. In the past, when we found derivatives with respect to x, it was written in terms of x, so all we had was x's in that expression. Now when we do implicit differentiation, we may get derivatives with respect to x and y, meaning that we might have x's and y's in our derivatives. So if we wanted to, say, find the slope of that circle at the point 3, negative 4, we can use this derivative we found here using implicit differentiation and just plug in 3 for x and negative 4 for y and get that. So what we're going to do is we're going to evaluate the derivative dy dx at that point 3, negative 4, and that will be the opposite of our x value, so negative 3 over the y value, negative 4. And that tells us the slope of that circle at the point 3, negative 4 is going to be positive 3/4. These steps can be found in section 3.7 of your book, and these are the steps that you would find to find the derivative of y with respect to x for any relation, whether it's a function or not. And we could use this process to find the derivative of any variable with respect to any variable. So it doesn't have to be y and x, but it could be position with respect to time, or really any variable. So we could replace x with t here, and we would replace then all of the x's with t's in different places and differentiate with respect to time rather than with respect to x. So this is a process that will work with any variables, not just x and y. We can use the same idea to differentiate at a higher level, to take the second or third or fourth derivatives of relations that are not functions. And we would start this exactly the same way. Let's say that we want to find the second derivative of y with respect to x. Then what we would do is we would start with the first derivative, which we've already found, dy dx is equal to negative x over y. And we would do the exact same thing. We would differentiate each term on its own. Differentiating the left side, this first term here, with respect to x, we would get exactly what it is we're looking for, the second derivative of y with respect to x. And on the right side, we would end up having to use the quotient rule because we have a function divided by a function. If you remember the quotient rule here, we are going to take the bottom times the derivative of the top, low d high, so y times the derivative of the top, which would be negative 1, and anytime we take the derivative, we're going to write the derivative with respect to what? So in this case, we're taking the derivative of x with respect to x, minus high d low, negative x, times the derivative of the bottom, the derivative of y. Now remember, we're going to take the derivative of y as if it's a function of y, and the derivative of y would be 1, but we took the derivative of y with respect to x. And that's all over the square of what's below, all over y squared. Now what we end up with here is 1 for dx. However, we do have the derivative of y with respect to x. And when we're finding this second derivative, we don't want to leave the first derivative in our answer. So I'm going to do a couple of things here in this next step. I'm going to simplify. So negative 1 times y is going to be negative y. And we have the opposite of negative x is going to be positive x. So we're going to have plus x times the derivative of y with respect to x, which is this right here. So we're going to plug the negative x over y in for the first derivative here. So we have negative x over y, and that is all over y squared still. So doing a little bit of simplification here, we could simplify this in a few different ways. Simplifying here, we would get negative y minus x squared over y all over y. This is an answer that would be acceptable. In fact, this answer would be acceptable in a free response section of a test. However, if this were in a multiple choice section of a test, you may have to simplify in different ways so that it matches up with one of the choices. So if we're finding higher order derivatives, a couple of things to keep in mind. First is that the first derivative, dy dx, should not be in your answer for a higher order derivative. Another thing we want to keep in mind is that second and higher order derivatives might be used, they may be written in terms of x and y, but the original function might often be able to be used to simplify the expression for the higher order derivative. And this would be useful when we have to match an answer to a multiple choice response. To illustrate that second note, let's look at the example that we just finished doing. We got that the second derivative of y with respect to x is equal to negative y minus x squared over y all over y. And what we're going to do is we're going to manipulate this, and actually we're going to try to rewrite it as a simpler expression. The first thing I would do if I were trying to do that is, looking at the top here, we could get a common denominator of y, and we could rewrite this. I'm sorry, this should be y squared here. I believe we had that wrong in the last example. All over the square of what's below, that should have given us y squared. So to get a common denominator there, we get the second derivative of y with respect to x is going to equal negative y squared minus x squared all over y. And I got that just by getting a common denominator here, multiplying this by y over y, and that's still all over y squared. A little bit more simplification here, we would get then that that is equal to the opposite of y squared plus x squared all over y to the third power. Now you may notice in this expression now we have x squared plus y squared, and in the original function we knew that x squared plus y squared is equal to 25. So what we can do now is we can replace the x squared plus y squared in this expression with 25, because we know that that is equal to 25. So the second derivative of y with respect to x is equal to negative 25 over y to the third power. It is likely, if you were taking a multiple choice test, that this would not be one of the options as the second derivative of this relation, but this would be. So you would have to be able to manipulate this into a form that looks like this. And understand that you have to use the original relation x squared plus y squared equals 25 to do so.